in an experiment.
We don't know yet.
Why is light so fast?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This time, the origin of Stonehenge's mysterious altar stone,
and how chemists have found a new way to break chemical bonds. I'm Dan Fox.
and I'm Nick Petrochow. Over 4,000 years ago, the ancient people of Britain took on a monumental task. They took stones weighing several tons, hundreds of miles across Britain, from the Preseli Hills in southwest Wales all the way to Salisbury Plain, to form part of what is now known as Stonehenge. Why these ancient people went to such lengths for these stones is still unclear. But it turns out this probably isn't the furthest afield they went.
The most similar rock in the UK that it might have come from was in northeast Scotland, the Orcadian Basin.
This is Anthony Clarke from Curtin University in Australia, speaking about Stonehenge's altar stone, a 6-ton stone that lies somewhat buried in the centre of the rock circles that make up the monument. The altar stone has been a puzzle for archaeologists for a long time. Despite its name, it's unclear whether it was actually used as an altar, and while it now lies flat with another stone fallen on top of it, it may have once stood upright. There's a lot researchers don't know about this stone, but it's bigger than many of the other stones and has a very central location, which suggests that it was significant to the builders of Stonehenge. And another mystery surrounding this stone is where it's from.
There's been a few ideas in the past decades. It was long thought to have come from the Preseli Mountains in Wales. Recent work moved away from that interpretation towards a source from the Brecon Beacons, a bit closer to Stonehenge. But recent work comparing the chemistry of rocks in the Brecon Beacons to the altar stone has moved away from that. So as of last year, the ultimate source of the altar stone really was an unknown question.
Before we get to the new analysis of the altar stone, it's maybe worth talking about Stonehenge in a little bit more detail. Around 10,000 years ago, there's evidence that Stonehenge was marked not with stone, but with wooden posts, perhaps indicating that the site was already important to the ancient peoples. Then, around 6,000 years ago, a round ditch was constructed, the first signs of the familiar circular structure. It's around this time that it's thought that a set of stones, known as the Blue Stones, arrived at Stonehenge from the Preseli Hills in Wales, a journey of some 150 miles. These were eventually arranged to make an inner circle of stones, but it wasn't until a few hundred years later that Stonehenge really started to take shape in the way that we know it today. That's when the huge 7-metre tall sarsen stones were brought to the site and raised up into the iconic circle of arches. It's thought that these massive slabs came from quite close by, maybe only 15 miles away. It's not clear when the altar stone itself was brought to the site, with theories suggesting it arrived with the bluestones from Wales, or with the Sarsens a few hundred years later. Last year, a detailed analysis ruled out a Welsh origin for the altar stone, so until now, its origin has remained a mystery. Anthony and a team of geologists and geochemists set out to solve this mystery and to discover where the altar stone is really from. Something that's not easy for this kind of rock.
The altar stone is unique in terms of Stonehenge in that it's made of a sandstone. So it's composed of lots of minute microscopic grains clumped together, cemented together to form a cohesive rock. The other blue stones are what we call igneous rocks. They form from cooling and crystallizing magma. They're a bit more straightforward to kind of compare because they will have one age, the age at which they froze to form the rock. But when a rock is made of lots of component parts, it definitely complicates interpretations.
But Anthony had a stroke of luck on his side. A rare opportunity to study a sample from the altar stone itself.
It's in many ways, it was quite a happy accident. I emailed a Welsh professor at Aberystwyth University to work on some other rocks from Wales that he had some expertise on. And he suggested, hey, we have this sample, we have these samples of the altar stone, and you have these amazing tools down under in Australia. Why not see what you can get from them, what information you can glean from these precious samples?
Nowadays, sampling from Stonehenge is impossible. It's a protected monument. But it wasn't always treated with so much reverence, and Richard Bevins, one of the other authors on the paper, had a sample taken from the altar stone back in 1844. He sent part of that sample to Anthony in Australia, where he could analyse the rock grain by grain with a specialised mineralogy tool and combined that with electron microscopy and mass spectroscopy to get a detailed analysis of the chemistry of the rock.
And from that chemistry, we can work out the ages and compare them to other source regions in the UK.
So, with the chemistry of the rock in hand, Anthony just had to go about the simple task of finding where, in the whole of Britain, were rocks that matched the altar stone.
The geology of Britain and Ireland is very complicated given it's quite a small area. But when we work out the ages of grains within the altar stone, this gives us, in a way, a data set. It gives us a barcode of numbers, if you will. We can then take this unique fingerprint of the altar stone and compare it using statistics to other basins, other sedimentary rocks within the UK. And unfortunately, you can't say if something is like another thing, you can just say it's different using statistics. And when we did that, the most similar rock in the UK that it might have come from was in northeast Scotland, the Orcadian Basin.
The Orcadian Basin is a region of sedimentary rock in the northernmost part of Scotland, covering the island of Orkney, part of the Shetland Islands, and the very tip of mainland Scotland. Some 600 or so miles away from Stonehenge. David Nash, a researcher who has looked at the provenance of some of the other stones from Stonehenge, but who wasn't involved in this work, was quite surprised at how far it seems that the altar stone has travelled.
The long-standing idea has been that the blue stones, including the altar stone, probably came from somewhere in South Wales. Now, I've been following the various studies that have been looking at whereabouts the altar stone might come from pretty closely. And one of the more recent ones has kind of discounted that South Wales source. So I was kind of waiting for the next paper. I think what this study does really nicely is it does a good job of knocking out areas that the altar stone couldn't come from.
Now, whilst David agrees that, based on this analysis, it seems that the altar stone came from Scotland, he doesn't rule out the possibility that it may have made part of its journey without human intervention.
The authors kind of discredit the idea that these stones might have been transported by glaciers. So, one possibility is, well, maybe these are what we refer to as erratics. In other words, they're large blocks of stone that maybe were transported by ice. And certainly I agree with them that it's unlikely that stone from the Orkneys was transported all the way to Stonehenge by ice. But there's no reason why it may not have been transported part of the way by ice. So there's pretty good evidence of old red sandstone erratics in North Yorkshire, in the Holderness area, where they find them coming out of the cliffs there that are made up of glacial sediments. I've not seen any evidence for really big pieces of old red sandstone in that area, though. But I don't think you can entirely discount the idea that at least partially they may have been moved by ice at least a little way south.
And whilst this paper focuses on the origin and geology of the rocks, it does raise a lot of questions about how connected the Neolithic people were in the time of Stonehenge.
So there's good evidence that things like cattle were transported. So I guess the argument is, why would they potentially not have also transported stone? Although this does seem like an incredibly long way. So you have to ask questions about why, what might have been the connection between the north of Scotland and the Stonehenge area.
Anthony also has a lot of questions that he'd like to answer about the altar stone. But for now, he's got something else that's a bit more immediate at hand.
I think I'm looking forward to finishing my PhD. I submit next month, so I'll get that out of the way. And then looking forward, I would really love to narrow down the source of the altar stone. We have this basin scale view. We know it came from the Orcadian Basin. But where within this rather large area of northeast Scotland? Did it come from the mainland? Did it come from Orkney? There's lots of unknown questions, and it would be amazing to perhaps one day find the precise quarrying site or source or outcrop that the altar stone came from.
One thing is for sure, though. This won't be the end of the mysteries that Stonehenge holds. In this podcast piece, you heard from Anthony Clarke from Curtin University in Australia and David Nash from the University of Brighton here in the UK. For more on Stonehenge's mysterious altar stone, check out the show notes for some links, including a link to a video we've been making. A nice way to also see what the altar stone looks like.
Coming up, breaking and making bonds is the business of chemistry, and now chemists seem to have found a new way to do it. Right now, though, it's the research highlights with Emily Bates.
A parasite that can be transmitted to humans through cat faeces or undercooked meat could be used to deliver complex proteins to the brain. Drugs made of large proteins, such as antibodies, cannot easily cross the blood-brain barrier, which limits their therapeutic effects. But Toxoplasma gondii naturally infiltrates the protective barrier to travel from the gut to the brain. Researchers engineered the parasite to produce therapeutic proteins of various sizes, and found that these parasites could carry several large proteins at once into human neurons growing in laboratory dishes. It's possible these modified Toxoplasma gondii could improve the delivery of protein-based treatments, such as those designed to replace abnormal proteins that result from certain genetic diseases. Absorb the full paper in Nature Microbiology. The Olympics are over for another 4 years, but the science of sport continues, as researchers have been discovering a skateboarder's optimal movements. It's known that skateboarders gain extra speed by squatting and then standing up at the right time as they go up and down half pipes, a movement known as pumping. So researchers created a computer model of these movements to identify the change in posture over time that provides the most acceleration. Corroborating their findings through observations of 2 skateboarders with different skill levels, the team found the pumping technique of the more experienced individual aligned more closely with the optimal curve than that of the less experienced person. If you're interested in that paper, you can get on board at Physical Review Research.
Next up, chemists have cracked breaking bonds in a way they've been trying to do for decades. When chemists want to synthesize new molecules, they take their starting materials and react them together by a series of steps to create the target compound. Through this, specific bonds between atoms are broken, while others are left intact, so you only make bonds in the desired places. For example, when you burn a propane grill, bonds between carbon, hydrogen and oxygen are broken from the gas and the air to end up with new compounds, carbon dioxide and water. Now, chemical bonds are made by atoms sharing electrons. and when they're broken, they can split up the electrons evenly or unevenly between them. And sometimes they don't end up sharing the electrons in ways that synthetic chemists like. Take selenium-selenium bonds. These tend to break evenly, sharing their electrons in equal numbers. But really, a lot more chemical reactions would be available if they were to break a bit more unevenly. And the same goes for many other compounds. Now though, a team in Nature has described an unconventional method for breaking selenium-selenium bonds that allows them to split up unevenly, and so could open up new ways of creating molecules. Anand Jagatir spoke to author Alexander Brader about the work, and started by asking him what his approach was to break selenium bonds unequally.
That's actually not so trivial because physically there is no driving force for this particular bond to split in that manner. So what we came up with is to let the bond split in its natural way evenly, but make sure that the resulting fragments, these fragments we call radicals, remain in close contact to one another. So if you shine the light at one of those radicals, it gives away its electron to the other one.
Okay, so it's kind of like a two-step process, but you end up at the end of it with this unequally broken bond, essentially.
Exactly. This is something that has to take place in two individual steps. But in order for this to work, many important things need to basically come together and just act in concert for the success of the reaction.
What was the secret to the success of this reaction then? What were the conditions that meant that this process worked?
The success of the reaction was dependent on the solvent that we ran the reactions in that provided reaction products in very good yields. And so our starting hypothesis, which turned out to be sort of correct, was that in this solvent, the two radicals that are formed when the bond between the two selenium atoms is evenly split, these radicals stay together for quite some time. And it's enough time for one of the two radicals to absorb light. And the solvent helps to not let these two radicals diffuse apart. That's one thing. The second reason why this solvent was so useful to us is that in the moment when the electron transfer takes place, we generate a pair of ionic species, one positively charged, one negatively charged. Under typical circumstances, if nothing else happens, these two differently charged species come back together and just form the starting material. However, in that solvent that we are using, the negatively charged species will receive a proton from the solvent, and therefore the recombination doesn't take place. And the positively charged species, this will then live for a while in that solvent. It's stabilized in that solvent, which is the third aspect of the solvent that makes it so valuable to us, so that this positively charged species can then react with whatever we expose it to and that we want it to react with.
As a chemist, if you want to synthesize a molecule, there are all these steps. You have to make sure you cleave the right bond and then add it onto the right other thing. And you've only got these very tiny windows in which your species can react with something else. And normally, if bonds cleave in this equal way, it's not much use to you. Whereas if you can force them to cleave in this unequal way and then stabilize the ions that are produced, which either have 2 electrons or no electrons, that's great. That gives you an opportunity to then say, we can now react that with something else and then, create a new species.
Exactly. And there's one more aspect that makes it also from an overarching perspective very valuable. If you want to, let's say, make a bank transfer or something, these days, in order to make sure that nothing goes wrong with your bank transfer, there's something like a 2-step security. And this makes sure that only you as the owner of your bank account can do the bank transfer, right? And it's a little bit like this in our case as well. So what we want to do is address a specific bond. So this specific bond that we want to address needs to be susceptible to 2 different independent stimuli. One for the even cleavage of that particular bond, and the second one for the electron transfer. Not many bonds share all of these features at the same time. So by the combination of these 2 stimulations, we can make sure that pretty much only the one desired bond will react in the manner that we intend.
And if you think of a chemical synthesis as like a long series of steps, like a kind of a pathway through molecular space, actually this kind of gives you access to new routes through that space. And actually you can do reaction combinations that you couldn't do before. And in theory, synthesize molecules that we aren't able to currently synthesize.
This is what we envision as a long-term perspective. I mean, what we basically accomplished right now was just to show that there is the possibility of making it. And now one has to think of how to implement it into synthetic strategies. And here I'm very much hoping for the chemical community to look at our concept and maybe implement it into their strategies.
I know this was just a sort of proof of concept, really. You wanted to see whether it was even possible to break bonds in this way. You've shown that in the paper, but what's sort of next? So what are some of maybe the limitations of this specific approach, and how are you hoping to tweak it in the future to sort of streamline it and make it better?
So from what we can tell as of now, this seems not necessarily limited to just selenium-selenium bonds or even carbon-selenium bonds. Probably this can be applied to a whole array of different element-element combinations, as long as they have a bond that is, for instance, symmetric and that can be split in an equal manner, and then will be susceptible to photoexcitation. So carbon or silicon, or maybe for copper-copper bonds or nickel or anything else interesting from the periodic table that we can get our hands on. And then in a very long-term approach, we would also be interested in looking at whether this can be inverted. So can you just choose which of the two fragments will receive both of the electrons simply by choosing, let's say, the wavelength you use to shine the light? Those questions would be really interesting and would have a severe impact on the way we do synthesis.
That was Anand Jagatir speaking to Alexander Breda from the University of Regensburg in Germany. For more on that story, check out the show notes for some links.
And that's all for this week. We'll be back again next week with more news from the world of science.
In the meantime, you can keep in touch with us on X, we're @NaturePodcast, or send an email to podcast@nature.com. I'm Dan Fox.
And I'm Nick Petrochow. Thanks for listening.